In 1781, William Herschel noticed a faint object moving against the background stars. It was first mistaken for a comet. It turned out to be a new planet, Uranus, doubling the known size of the solar system almost overnight. That planet rotates at a tilt of about 98 degrees. It does not spin upright like Earth, or even lean gently like Saturn. It rolls through space almost completely on its side. For decades at a time, one pole faces the sun directly. The opposite pole remains in continuous darkness. One full orbit around the sun takes 84 Earth years, so a single season there lasts about 21 Earth years. Time stretches differently on this world. It is colder than Neptune, even though Neptune orbits farther from the sun. Unlike Jupiter and Saturn, it releases almost no extra heat from its interior. By the usual rules of planetary physics, it should not behave this way. Its magnetic field is not centered within the planet. It is tilted at a strange angle, different from its spin, as if the internal structure does not align with the surface we observe. We have visited it only once. In 1986, a single spacecraft passed by and gave us most of what we still rely on today. Since then, no orbiter has returned, and yet planets of similar size appear to be common around other stars. In the wider galaxy, worlds like this may outnumber Jupiter-sized giants. We might be looking at one of the most typical kinds of planets in the universe, but what happened to tilt an entire planet onto its side? How does a world colder than its more distant neighbor produce so little internal heat? Why does its magnetic field twist away from its own rotation? And what does it mean if the planet we understand the least is the one that breaks the most established rules? Tonight, we examine Uranus and the forces that reshaped it. But before we begin, I would love to know in the comments where you are listening from and what time is it over there. I love seeing how far these science explorations travel. Now take a slow, deep breath. Let your shoulders relax, and together, let us follow the evidence that makes Uranus the strangest planet in our solar system. On a cold March night in 1781, beneath the steady air of Bath, England, a musician turned skywatcher adjusted the polished mirrors of his handmade telescope and let his gaze settle among the familiar constellations. William Herschel had mapped these stars many times before, tracing their positions with patient discipline, listening to the silence between them as if it were part of a score. Against that fixed arrangement, he noticed a faint point of light that did not quite hold its place. It drifted, subtly, almost politely, as though reluctant to disturb the order of the sky. At first, it seemed reasonable to assume it was a comet. Comets wandered. They carried soft glows and shifting paths. Herschel recorded its movement carefully, night after night, measuring its position against nearby stars. The object did not grow a tail. Its disk, under magnification, appeared steadier than a comet's haze. Its motion was deliberate, confined to a path that hinted at something larger and more structured than an icy visitor falling inward from the dark. Word of the observation traveled through the scientific circles of Europe. Calculations were made with ink and candlelight. Orbital predictions were compared with known cometary trajectories. Gradually, the conclusion emerged with quiet certainty. The object was not a comet at all. It was a planet, orbiting far beyond Saturn, occupying a region of space no known world had claimed. Until that moment, the solar system had seemed bounded by the slow ring of Saturn. The architecture felt complete, symmetrical, almost finished. Herschel's discovery extended that architecture outward in a single stroke. The known scale of the solar system expanded dramatically, not through speculation, but through direct observation. What had appeared as a distant ceiling became a threshold. This was the first planet ever discovered with a telescope. All previous planets had been known since antiquity, visible to the naked eye, woven into myth and early astronomy. Uranus entered human awareness through crafted glass and ground metal, through deliberate magnification. Its discovery marked a turning point in method as much as in geography. The heavens were no longer a fixed inheritance from the past. They became a landscape open to expansion through instruments, mathematics, and patient attention. The naming of the planet reflected that shift. Rather than drawing from Roman tradition alone, it reached further back to the Greek sky god Uranus, father of Saturn. The lineage symbolized depth, a step into an older layer of myth as the physical boundary of the solar system moved outward. Yet beneath the poetry of names lay a more profound transformation. If one unseen planet could exist beyond Saturn, others might as well. The solar system was no longer a closed diagram, but a system capable of surprise. Astronomers began refining orbital mechanics with renewed urgency. The gravitational relationships among planets were recalculated to include this new mass. Small irregularities in known orbits took on new significance, hinting that unseen influences might still be waiting in the dark. The discovery of Uranus did not merely add a new member to a list, it altered the expectations governing that list. In the centuries that followed, telescopes grew larger and theories more intricate, but the quiet moment in 1781 remained a threshold. A faint wandering light, once mistaken for a comet, revealed that the sky was deeper than assumed. Modern planetary astronomy traces part of its origin to that realization, when a careful observer recognized motion where others had seen only stillness, and the solar system quietly doubled in scale. Far beyond the warmth where sunlight still carries weight, Uranus occupies a category that reshaped how planetary scientists describe giant worlds. It is not grouped with Jupiter and Saturn despite its size and presence. Instead, it belongs to a quieter class known as ice giants, a term that speaks less to frozen landscapes and more to chemistry compressed under extraordinary pressure. In the early solar system, distance determined composition. Closer to the Sun, volatile compounds could not condense easily, leaving rocky material and lighter gases to define emerging planets. Farther out beyond the frost line, where temperatures fell low enough, water, ammonia, and methane could solidify into crystalline grains. Uranus formed in that colder reservoir, gathering these compounds in abundance. Over time, gravity drew them inward, building a planet whose bulk is dominated not by hydrogen and helium alone, but by substances once considered simple ices. The word ice here carries a different meaning than it does on Earth. Within Uranus, water does not resemble snow or frozen seas. Pressures millions of times greater than Earth's surface compress molecules into dense fluid states. Water, ammonia, and methane intermingle in a deep mantle that behaves neither like solid rock nor like a thin gas. It is often described as a slushy ocean, though even that analogy softens the intensity of its environment. Heat and pressure transform familiar chemistry into exotic forms, layered and dynamic beneath the clouds. Compared with Jupiter and Saturn, Uranus is modest in mass. It holds only a fraction of their gravitational dominance, and its diameter is smaller, though still vast by terrestrial standards. This reduced scale alters its internal architecture. Gas giants are dominated by thick envelopes of hydrogen and helium that extend inward toward cores under crushing weight. Uranus, by contrast, contains a thinner outer atmosphere beneath which lies a massive mantle rich in heavier volatile compounds. The proportions shift the balance of pressure, temperature, and convection throughout the planet. At its outermost boundary, a pale atmosphere drapes over the deeper layers. Hydrogen and helium still dominate there, but methane plays a visible role, absorbing red wavelengths of sunlight and lending the planet its muted cyan tone. Beneath that upper veil, clouds form in bands and layers, shaped by temperature gradients and slow atmospheric circulation. Yet there is no surface in the terrestrial sense. No shoreline or crust separates sky from ground. As one descends, gas thickens gradually into fluid and fluid into denser phases until the distinction between atmosphere and interior dissolves. The absence of a solid surface reshapes every physical process. Storms do not break against continents. Winds flow across a continuous envelope of material that deepens steadily. Any probe descending through the clouds would encounter increasing pressure without ever finding stable ground. The concept of standing, so natural on rocky worlds, has no meaning there. This classification as an ice giant is more than terminology. It reflects a fundamentally different blueprint for planetary construction. In Uranus, the materials that dominate are heavier, richer in oxygen, nitrogen, and carbon than the hydrogen seas of larger giants. Its gravity binds them into layers that conduct heat and electricity in unfamiliar ways, influencing magnetic fields and internal energy flow. The planet's strangeness begins not at the surface, but in the proportions of its building blocks, assembled in a distant, colder region of the early solar system, where ice was plentiful and gas alone was not enough. Long before its atmosphere settled into the muted tones we observe today, Uranus underwent a transformation written not in color or chemistry, but in orientation. Planets are born from rotating disks of gas and dust, inheriting a general alignment as they gather mass. Most retain that inherited posture, spinning with only modest inclinations, their poles angled gently as they orbit the Sun. Uranus diverges from that pattern in a way that reshapes its entire identity. Its axis is tilted by about 98 degrees, placing it nearly perpendicular to the plane of its orbit. Rather than spinning upright, it turns as if laid carefully on its side. This sideways rotation alters the geometry of sunlight in a profound way. As Uranus travels along its long orbital path, its poles alternately lean toward and away from the Sun. For extended intervals, one hemisphere receives continuous illumination, while the opposite hemisphere remains turned inward, receiving none at all. The equatorial regions experience a rising and setting sun that traces unusual arcs across the sky, moving in patterns that do not resemble those of any other major planet. The tilt is not a superficial feature. It reorganizes the distribution of energy across the entire globe. Such an extreme inclination is unlikely to have arisen quietly. In the early solar system, planetary formation was not a gentle process. Protoplanets moved through crowded regions filled with debris, colliding and merging as gravity shaped the emerging architecture. Computer simulations suggest that Uranus may have experienced a massive impact during this era, possibly involving an object comparable in size to Earth. A collision of that scale would have carried enough angular momentum to knock the young planet onto its side, altering its rotation permanently while leaving it otherwise intact. The evidence for this event lies not only in the tilt itself, but in the consistency of its current motion. Uranus rotates once every 17 hours, maintaining a steady sideways spin. Its equator is oriented almost vertically relative to its orbital path, yet the rotation remains stable over billions of years. This stability implies that whatever force acted upon it did so decisively, imparting a new axis that the planet then carried forward as it continued to evolve. The consequences of this orientation extend deep into its climate system, with poles alternately bathed in prolonged sunlight and then submerged in darkness. Temperature gradients develop in ways that differ from more upright planets. Atmospheric circulation adjusts to these prolonged imbalances, redistributing heat through complex flows that operate over decades. Cloud formation, wind patterns, and seasonal contrasts are all shaped by the angle at which sunlight arrives. The tilt determines not only where light falls, but how the planet responds internally to that illumination. Beneath the visible layers, the redistribution of energy influences convection within the mantle. The sideways posture affects how heat moves from interior regions toward the upper atmosphere, subtly guiding the pathways along which energy travels. Over immense spans of time, this orientation becomes woven into every dynamic process, from the motion of clouds to the behavior of deeper currents. Uranus does not simply lean, it inhabits a different geometric relationship with the Sun. The planet's sideways rotation stands as a reminder that the solar system's present order emerged from earlier turbulence. In that distant epoch, collisions could redefine a world's posture with a single encounter. The roll of Uranus through space carries that ancient memory forward, preserved in the angle of its axis, and in the quiet, persistent spin that continues today. There are moments in its long orbit when the Sun seems to hesitate above one horizon and refuse to move. On Uranus, this is not a brief illusion of high-latitude summer, but a planetary condition that unfolds over decades. Because the planet's axis lies nearly in the plane of its orbit, its poles take turns facing the Sun almost directly. When one pole tilts inward, it enters a season that lasts roughly 42 Earth years, bathed in uninterrupted daylight. Across the globe, the opposite pole recedes into a night of equal length, a darkness that endures for another 42 years before the balance slowly reverses. This arrangement reshapes the very meaning of a day. Uranus still completes a rotation in about 17 hours, turning steadily as it travels around the Sun. Yet, during these prolonged solstitial periods, the rotation does not produce familiar cycles of sunrise and sunset at the poles. Instead, the Sun traces tight circles in the sky, hovering above the same hemisphere without ever dipping below the horizon. The light changes in angle and intensity as the decades pass, but it does not disappear. On the far side, the sky remains star-filled and cold, with the Sun absent for a human lifetime. As the planet continues along its 84-year journey, the geometry shifts. The once illuminated pole gradually leans away, and the equatorial regions move into a transitional phase where both hemispheres share light more evenly. It is during these equinox periods that the entire globe experiences alternating days and nights, though even then the solar path is unlike that of any other major planet. At the equator, the Sun rises and sets in sweeping arcs that curve almost vertically, moving from horizon to horizon in a way that defies terrestrial intuition. The sky's motion appears rotated, as though the familiar compass of up and down has been quietly redefined. These extended cycles generate extreme seasonal contrasts. When a pole faces the Sun for decades, energy accumulates gradually in the upper atmosphere. Temperatures respond slowly, influenced by the deep layers beneath the clouds, and atmospheric circulation adjusts over spans measured not in months but in generations. The hemisphere in darkness cools steadily, its clouds and winds shaped by the prolonged absence of solar input. The imbalance between light and shadow becomes a defining feature of the climate, imprinting patterns that evolve with deliberate patience. No other planet in the solar system experiences such a prolonged alternation of hemispheric illumination. Earth's tilt produces seasons that feel significant to us, yet they unfold within a single year. Even the more modest inclinations of Mars or Saturn create variations that are brief compared with Uranus. Here, a single season stretches across 21 Earth years, and the full cycle of daylight and darkness at one pole spans nearly the entirety of a human lifespan. Within this framework, the concept of time acquires a different rhythm. Weather systems emerge and dissipate under lighting conditions that remain stable for decades. Subtle changes in brightness and temperature ripple through the atmosphere, guided by the slow progression of the orbit. The sideways orientation, established long ago, expresses itself most visibly in these prolonged days and nights, where sunlight does not simply warm a hemisphere, but claims it entirely, then relinquishes it just as completely. Time, on Uranus, unfolds with an almost geological patience. While Earth completes its journey around the Sun in a single year, Uranus requires 84 Earth years to trace its full orbit. This elongated path through space stretches the cadence of change, turning what would be a brief seasonal transition elsewhere into an era that can span a significant portion of a human life. Each season lasts about 21 Earth years, shaping the planet's atmosphere not in quick pulses, but in slow, deliberate adjustments. As the planet advances along its orbit, sunlight migrates gradually from one hemisphere to the other. The shift is subtle at first, measured in fractional changes of solar angle that accumulate over years. Because the atmosphere is deep and the internal heat source is comparatively weak, the response to these shifts is restrained. Temperatures do not swing abruptly. Instead, they evolve with measured restraint, guided by the slow redistribution of energy across layers of gas and volatile compounds. Observations from Earth and from space-based telescopes have revealed that Uranus does not remain static during these prolonged intervals. Over decades, faint cloud structures emerge in regions that were once relatively featureless. Bright patches form, then fade, as if the atmosphere were testing new configurations. These changes are not fleeting storms that vanish overnight. They persist, altering the planet's appearance over spans of years. The long seasons provide enough time for atmospheric circulation patterns to strengthen, weaken, and reorganize in response to the gradual realignment of sunlight. Near equinox, when both hemispheres receive more balanced illumination, activity appears to increase. Subtle bands become more distinct. Transient cloud systems brighten against the pale backdrop. Winds, already swift, interact with temperature gradients that have been building for decades. Yet even these moments of comparative dynamism unfold with a calm deliberation. The processes are extended, stretched across time in a manner that reflects the planet's slow orbital rhythm. The persistence of each season influences how energy is stored and released within the atmosphere. Prolonged sunlight allows upper layers to warm incrementally, while deeper regions respond even more slowly. When darkness follows, cooling proceeds with equal patience, the thermal inertia of the planet resisting abrupt change. This lag between illumination and atmospheric response contributes to complex patterns that may not align perfectly with the immediate position of the sun. The visible state of the atmosphere can reflect conditions established years earlier, carrying a memory of prior alignment. Over the course of a single Uranian year, observers on Earth can witness only a fraction of this cycle. Entire seasonal arcs extend beyond the duration of most scientific careers. As a result, the record of change has been assembled gradually through careful monitoring and comparison across decades. Each new image becomes part of a long continuum, adding nuance to the understanding of how a tilted ice giant breathes in light and exhales it in measured, delayed responses. In this extended framework, The concept of season expands beyond familiar definitions. It becomes a slow migration of illumination across a world whose orientation and composition conspire to temper immediacy. Clouds gather and disperse with unhurried grace, shaped by forces that operate on timescales uncommon among planets. The result is a climate that moves not in sharp transitions but in prolonged phases, each lasting long enough to feel almost permanent before gradually yielding to the next. At the edge of sunlight's reach, where warmth arrives already thinned by distance, Uranus holds a distinction that seems almost counterintuitive. Despite not being the farthest major planet from the Sun, it possesses the coldest planetary atmosphere measured in the solar system. In its upper layers, temperatures can fall below minus 224 degrees Celsius, minus 371 degrees Fahrenheit, a depth of cold so extreme that molecular motion slows to a near stillness, and the concept of warmth becomes almost abstract. What makes this even more striking is that Neptune orbits farther from the Sun, receiving less solar energy overall. Yet at comparable atmospheric levels, Neptune does not descend to such low temperatures. The expectation would be simple. Greater distance should mean greater cold. Uranus quietly contradicts that expectation. Its thermal profile suggests that distance alone does not dictate atmospheric temperature. Something internal, something subtle, alters the balance. Measurements gathered during the brief flyby in 1986, along with later infrared observations from Earth orbiting instruments, reveal that Uranus emits very little excess heat. Most giant planets radiate more energy than they receive from the Sun, a remnant of formation and ongoing gravitational contraction. Jupiter and Saturn, for example, glow faintly in infrared wavelengths, releasing stored internal energy into space. Uranus, by contrast, appears nearly in equilibrium with the sunlight it absorbs. It contributes almost no additional warmth from within. This absence shapes its atmosphere in quiet but profound ways. Without a strong upward flux of internal heat, convection becomes muted. The deep layers do not vigorously transport energy toward the cloud tops. Instead, the atmosphere settles into a more stratified structure, where vertical mixing is restrained. Heat received from the Sun must travel downward and outward through a system that lacks the internal push found in other giant planets. The result is an energy imbalance that remains difficult to explain. Some models suggest that an ancient impact, the same event that may have altered its rotation, could have disrupted the interior in a manner that trapped heat at depth. If thermal energy became confined beneath stable layers, its escape into space would be slowed dramatically. Over billions of years, this could leave the upper atmosphere deprived of the supplemental warmth seen elsewhere. Another possibility involves the composition and structure of the interior itself. The mixture of water, ammonia, and methane under extreme pressure may conduct heat differently than the metallic hydrogen layers present in larger gas giants. Variations in how efficiently energy moves through these materials could influence how much warmth ultimately reaches the surface layers. In such a scenario, the planet's chemistry would not only define its classification as an ice giant, but also govern its thermal silence. The extreme cold shapes the behavior of gases at high altitudes. Methane condenses under these frigid conditions, forming thin hazes and cloud decks that reflect sunlight and further regulate temperature. Subtle interactions between radiation and atmospheric particles determine how energy is absorbed and re-emitted, creating a delicate equilibrium that persists across decades. Uranus does not blaze with internal heat. It does not radiate excess energy into the surrounding dark. Instead, it exists in a restrained thermal state, where the balance between incoming sunlight and outgoing radiation hovers close to neutrality. Within that balance lies one of its enduring puzzles, a quiet reminder that even among giant planets, not all interiors continue to whisper warmth into the cold expanse beyond. Deep within most giant planets, a quiet furnace continues to operate long after formation. Residual heat from gravitational collapse, combined with the slow compression of immense mass, drives energy outward through thick layers of gas. This process is subtle yet persistent. Jupiter releases more energy than it absorbs from the Sun, glowing faintly in infrared as stored warmth escapes into space. Saturn behaves in a similar way, its interior still shedding heat accumulated during its birth. Uranus stands apart in this regard. Measurements of its thermal emission reveal a near balance between incoming sunlight and outgoing radiation. It emits almost no additional internal heat. In the language of planetary physics, it appears almost inert, as though the internal engine that powers other giants has been quieted. This absence is not dramatic or explosive. It is simply a silence where activity might have been expected. The contrast becomes clearer when considering the scale of these worlds. All giant planets formed from collapsing regions of the solar nebula, converting gravitational energy into thermal energy as they gathered mass. Over time, that heat should gradually leak outward. In Jupiter and Saturn, this leakage remains measurable billions of years later. In Uranus, however, the outward flow seems unusually restrained. Its upper atmosphere shows little sign of vigorous convection driven from below. One proposed explanation traces back to the planet's early history. A massive collision, the same event that may have altered its rotation, could have profoundly reshaped its interior. If the impact redistributed material into stable layers, it might have created a configuration that traps heat more efficiently. Rather than allowing energy to rise freely toward the atmosphere, the interior could have become stratified, with compositional gradients that suppress vertical mixing. In such a structure, warmer material would remain confined at depth, insulated by overlying layers of different density. Another possibility involves the behavior of exotic fluids under extreme pressure. The deep mantle of Uranus, composed largely of water, ammonia, and methane in compressed states, may conduct heat differently from the metallic hydrogen found inside Jupiter and Saturn. Variations in thermal conductivity and convective efficiency could significantly influence how energy migrates outward. If these materials transport heat less effectively, the planet would cool more slowly at depth, while appearing thermally subdued at the surface. The missing internal heat has broader consequences. Without a strong upward energy flux, atmospheric dynamics rely more heavily on solar input. Circulation patterns develop under weaker internal forcing, potentially contributing to the planet's relatively calm appearance in earlier observations. The subdued heat flow also affects how magnetic fields are generated, since dynamo processes depend on the movement of electrically conductive fluids within the interior. Yet, despite decades of study, the precise reason for Uranus's thermal restraint remains uncertain. Models must account for the planet's composition, rotation, and possible impact history, weaving together gravitational physics and fluid dynamics across immense pressures. The result is not a single definitive answer, but a landscape of plausible mechanisms, each consistent with certain observations and incomplete in others. In the broader context of planetary science, Uranus offers a reminder that similar origins do not guarantee similar outcomes. Worlds born from the same protoplanetary disk can diverge in subtle yet consequential ways. Where Jupiter and Saturn continue to radiate stored warmth into the surrounding dark, Uranus holds its energy close, maintaining a delicate balance that challenges simple expectations and invites deeper exploration into the hidden architecture beneath its clouds. Color in the outer solar system is not decoration but chemistry made visible. When sunlight reaches Uranus, after traveling billions of kilometers, it encounters an atmosphere layered with hydrogen, helium, and trace gases that quietly determine what is seen from afar. Among these trace components, methane plays a decisive role. Though present in relatively small quantities compared with hydrogen, it shapes the planet's appearance with remarkable efficiency. Sunlight contains a spectrum of wavelengths, from longer red tones to shorter blue ones. As light passes through the upper atmosphere of Uranus, methane molecules absorb strongly in the red portion of that spectrum. Photons associated with red wavelengths are captured and converted into thermal energy, leaving less of that color to be scattered back into space. What remains, predominantly blue and green wavelengths, is reflected and diffused outward. The combined effect produces the planet's characteristic pale cyan tone, a color that appears almost uniform when viewed from great distance. This process unfolds high in the atmosphere, where methane exists as a gas mixed within the hydrogen and helium envelope. At colder temperatures, methane can condense, forming thin cloud layers that further influence how light interacts with the planet. These clouds do not form a continuous blanket. They assemble in stratified sheets and localized structures suspended within a broader haze that softens contrasts. The result is a muted, almost velvety appearance, lacking the bold banding visible on some other giant planets. Beneath the upper haze, additional cloud decks may exist at varying pressures and temperatures. Some are thought to contain methane ice crystals, while deeper layers could incorporate compounds such as hydrogen, sulfide, or water in compressed states. Each layer subtly modifies the path of incoming and outgoing radiation. Light that penetrates the upper methane-rich region can scatter within lower clouds before emerging again, slightly altered in brightness or hue. These interactions contribute to the planet's overall softness of tone. The relative uniformity of Uranus's color once led to the impression of a featureless world. Early images revealed few strong contrasts, reinforcing the idea of a calm and unchanging atmosphere. Yet more sensitive observations have detected faint bands and transient bright spots, indicating that the haze conceals dynamic processes below. Even so, the dominance of methane absorption ensures that red light remains suppressed, maintaining the planet's cool palette across decades of observation. In comparison with Neptune, which shares methane as a key atmospheric constituent, Uranus appears slightly paler. Subtle differences in haze thickness and atmospheric mixing likely account for this variation. The interplay between methane concentration, cloud altitude, and vertical circulation determines how deeply sunlight can penetrate and how efficiently specific wavelengths are removed. Small adjustments in these factors can shift the balance between deeper blues and softer greens. The cyan glow of Uranus, therefore, is not a surface feature but an atmospheric signature. It reflects the composition and temperature structure of the outer layers, shaped by the same chemistry that defines its classification as an ice giant. Light arriving from the sun is filtered, selectively diminished, and then returned to space in altered form. What observers see is the cumulative result of countless molecular interactions, each absorption and scattering event contributing to a color that has become synonymous with this distant world. From a distance, Uranus once seemed almost serene, Early telescopic views revealed a smooth, nearly uniform disk, its pale cyan surface lacking the bold stripes or swirling vortices seen elsewhere. Even when Voyager 2 swept past in 1986, the images it transmitted showed a planet that appeared subdued. Only a few faint clouds were visible, and broad atmospheric features seemed muted, as though the world were wrapped in a quiet stillness. That impression lingered for years. Compared with the turbulent belts of Jupiter or the dynamic storms of Neptune, Uranus appeared restrained, almost inert. Its atmosphere seemed to offer little drama, a calm sphere rotating in silence. Yet this appearance was shaped in part by timing. When Voyager 2 arrived, the southern hemisphere was angled toward the sun in a prolonged season, and the distribution of sunlight may have suppressed the contrast of visible features. Subtle structures can disappear beneath a uniform haze when lighting conditions remain steady for decades. As observing technology improved, and as Uranus progressed along its orbit, a more complex picture began to emerge. Powerful ground-based telescopes, equipped with adaptive optics, along with space telescopes, sensitive to infrared wavelengths, revealed transient bright spots and elongated cloud systems. These features did not dominate the globe, but they demonstrated that beneath the soft exterior lay a dynamic atmosphere capable of rapid change. Wind measurements derived from tracking cloud motions indicated speeds exceeding 500 miles per hour. These winds flow primarily in zonal patterns, moving parallel to lines of latitude, and in some regions they travel opposite to the planet's rotation. Such velocities rival those found on Neptune and exceed many atmospheric currents on Earth by a wide margin. The apparent calm of the visible disk conceals these swift streams of gas racing around the planet in steady bands. Occasionally, the atmosphere produces sudden bright cloud eruptions. These features can appear unexpectedly, rising through the upper haze and reflecting more sunlight than their surroundings. Some persist for weeks or months, drifting with prevailing winds before fading. Others dissipate more quickly, leaving only faint traces in subsequent observations. Their emergence suggests localized upwellings from deeper layers where differences in temperature or composition drive vertical motion. Infrared imaging has been especially revealing. At wavelengths beyond visible light, temperature contrasts become clearer, exposing structures hidden to ordinary cameras. Regions that seemed uniform in earlier images show variations in thermal emission, indicating that the atmosphere is layered and active. The interplay between sunlight, internal structure, and atmospheric chemistry creates patterns that are subtle but persistent. The contrast between outward appearance and underlying motion defines this stage of understanding. Uranus does not display its turbulence in bold, colorful bands. Instead, it operates beneath a veil, where winds accelerate and clouds form without announcing themselves dramatically. The earlier perception of stillness arose not from a lack of activity, but from the difficulty of perceiving it through distant instruments and seasonal geometry. As decades pass and lighting conditions evolve, the planet reveals more of its character. The calm that once defined it in images has given way to recognition of a complex, energetic atmosphere. Beneath the muted tones and softened edges, powerful winds and transient storms continue their work, shaping a world that is quieter in appearance than in motion and more intricate than first impressions allowed. Invisible lines thread outward from Uranus, extending far beyond the soft haze of its atmosphere into surrounding space. These lines trace the planet's magnetic field, a structure shaped by movements deep within layers no instrument has directly seen. When Voyager 2 measured this field, during its brief passage, the data revealed a geometry unlike that of any other major planet explored at the time. On Earth, the magnetic field is tilted modestly relative to the planet's rotation axis, and its center lies close to the planet's physical center. Jupiter and Saturn display similar coherence, their magnetic dipoles roughly aligned with their rapid spins. Uranus departs sharply from this pattern. Its magnetic field is tilted by about 59 degrees relative to its rotation axis, and the magnetic center is significantly displaced from the planet's geometric core. The dipole does not pass neatly through the middle. Instead, it appears offset, as if anchored in a region removed from symmetry. As Uranus rotates, this misalignment produces a dramatic wobble in the magnetosphere. The magnetic poles sweep through space in wide arcs, carrying charged particles along shifting paths. From an external perspective, the magnetic environment around the planet changes orientation over the course of a single rotation. Radiation belts twist and reform, and the interaction with the solar wind varies continuously as different regions of the field face outward. The consequences of this configuration are subtle yet profound. Auroral emissions, generated when charged particles spiral along magnetic field lines toward the atmosphere, do not form stable ovals centered neatly on geographic poles. Instead, they can appear at unusual latitudes, shifting as the field rotates. The magnetosphere stretches and contorts, shaped not only by the pressure of the solar wind, but by the intrinsic asymmetry of the field itself. This peculiar structure offers clues about the processes occurring deep inside the planet. Magnetic fields arise from dynamo action, the movement of electrically conductive fluids within a rotating body. In Earth, this motion occurs within a molten iron outer core. In Jupiter, metallic hydrogen, under extreme pressure, conducts electricity and drives the field. Uranus, however, lacks the vast metallic hydrogen region present in larger gas giants. Its interior is believed to consist of layers rich in water, ammonia, and methane under immense pressure, forming exotic fluids capable of conducting electricity in unfamiliar ways. If the dynamo operates within a relatively thin shell rather than a central core, the resulting field could naturally be offset and highly tilted. Computer models suggest that convection in these intermediate layers, combined with the planet's sideways orientation, may generate a magnetic dipole that is both displaced and inclined. The field's geometry becomes a reflection of the planet's internal architecture, shaped by composition and pressure rather than by simple symmetry. Because the magnetic axis and rotation axis are so misaligned, the magnetosphere experiences a continuous reconfiguration. Charged particles trapped within it trace paths that shift with each rotation, producing a complex and dynamic environment. The wobble does not signal instability in the sense of collapse. Rather, it represents a stable but unconventional equilibrium, maintained over vast spans of time. Uranus thus carries not only a tilted axis and unusual seasons, but also a magnetic signature that resists expectation. Its field does not align neatly with its spin, nor does it originate from a centered core in the way many models once assumed. Instead, it emerges from deeper layers, arranged in ways that challenge simple geometric intuition, adding another quiet irregularity to a world already defined by departures from the ordinary. Beyond the visible atmosphere, where sunlight thins into a sparse wind of charged particles, Uranus extends an unseen boundary that shifts with restless geometry. This boundary, known as the magnetosphere, forms where the planet's magnetic field meets the solar wind streaming outward from the sun. Around many planets, this region assumes a relatively stable configuration, compressed on the sunward side and drawn into a long tail on the nightward side. Around Uranus, the structure is anything but simple. The magnetic tail stretches millions of miles into space, carried away from the sun by the pressure of the solar wind. Yet, because the magnetic field itself is steeply tilted and offset, the tail does not trail neatly behind the planet in a single, steady line. Instead, it twists as Uranus rotates, spiraling in response to the misaligned dipole sweeping through space. Each 17-hour rotation reorients the magnetic field relative to the solar wind, causing the magnetosphere to flex and reconfigure in a continuous cycle. This produces a shape unlike those observed around other planets. Rather than a stable, comet-like form with a fixed orientation, Uranus's magnetosphere resembles a corkscrew pattern wound by the planet's sideways posture and rotating magnetic axis. The field lines wrap and unwrap, creating a dynamic environment where charged particles experience changing pathways over short timescales. The magnetotail can fold back upon itself, its structure evolving as the planet turns. The sideways rotation amplifies this complexity. Because the planet's rotational axis lies nearly in the plane of its orbit, the orientation of the magnetosphere relative to the Sun changes dramatically over the course of a Uranian day. At certain points, the magnetic poles can point almost directly toward or away from the Sun, altering how solar wind particles enter and interact with the field. At other times, the field lines align differently, reshaping the distribution of energy within the surrounding space. These shifting geometries influence the behavior of auroras. On Earth, auroral displays cluster near geographic poles, tracing relatively stable magnetic ovals. On Uranus, the auroral emissions appear at unusual latitudes, guided by a magnetic field that does not coincide with the rotational poles. As the planet turns, the regions where charged particles precipitate into the atmosphere migrate, producing emissions that can shift in position over short intervals. Observations in ultraviolet wavelengths have captured these faint glows, revealing patterns that defy simple symmetry. The magnetosphere also governs the trapping and acceleration of energetic particles. Electrons and ions spiral along magnetic field lines, gaining and losing energy as the field stretches and twists. Radiation belts form within this environment, yet their structure is influenced by the constant reorientation of the magnetic axis. The result is a radiation system that is both stable over long periods and variable over the course of each rotation. Uranus therefore presents not merely a tilted magnetic field, but a magnetosphere in perpetual adjustment. Its tail extends vast distances into space, yet its form is continually reshaped by rotation and asymmetry. The surrounding environment is neither chaotic nor fixed. It is rhythmic, cycling through configurations as the planet spins. In this interplay between solar wind and misaligned magnetism, Uranus reveals another layer of its complexity, an invisible architecture that moves in concert with its unusual orientation and quietly distinguishes it from every other giant planet. For much of the 20th century, rings were thought to belong almost exclusively to Saturn, their bright arcs forming one of the most recognizable structures in the solar system. Uranus, distant and understated, was not widely expected to possess such adornment. Its muted disk gave no obvious hint of surrounding structure. Yet, in 1977, a subtle flicker of starlight revealed something unexpected. Astronomers were observing Uranus as it passed in front of a distant star, an event known as a stellar occultation. As the planet approached the star's position in the sky, the starlight dimmed in small, precise steps before the disk itself moved across it. These brief, symmetrical dips occurred both before and after the main occultation, indicating that material encircled the planet in narrow bands. The pattern could not be explained by atmosphere alone. Uranus possessed rings. Subsequent observations confirmed the discovery. Rather than broad, luminous sheets like those of Saturn, the rings of Uranus were thin, dark, and sharply defined. They appeared as narrow ribbons composed of small particles, reflecting only a modest fraction of the sunlight that reached them. Their darkness suggested material rich in carbon or other radiation-altered compounds, surfaces that had been exposed to space long enough to lose brighter volatiles. The system consists of multiple distinct rings, each separated by clear gaps. Some are only a few kilometers wide, yet they maintain remarkable coherence as they orbit. The particles within them range from dust-sized grains to larger fragments, moving along paths governed by the planet's gravity. Shepherd moons, small satellites positioned near the edges of certain rings, help confine the material, preventing it from dispersing into a diffuse disk. Compared with Saturn's expansive rings, which span hundreds of thousands of kilometers and gleam with icy brightness, Uranus's rings seem restrained. They are closer to the planet and less reflective, their structure more akin to a set of delicate wires encircling the globe. This difference reflects both composition and history. While Saturn's rings are dominated by water ice, the darker hue of Uranus's rings implies a distinct origin or subsequent evolution under harsher radiation conditions. One prevailing idea suggests that the rings may have formed from the remnants of shattered moons. In the distant past, a collision between a satellite and another object could have fragmented the moon, scattering debris into orbit. Over time, gravitational interactions would sort this material into narrow bands. Alternatively, tidal forces exerted by Uranus might have disrupted a small body that wandered too close, pulling it apart within a region where gravity overcomes structural cohesion. Voyager 2's flyby in 1986 provided the first close images of the rings, revealing additional faint components and confirming their intricate structure. Later observations from Earth-based telescopes and space observatories expanded the catalog, identifying more tenuous outer rings and dusty halos. Even so, the system remains comparatively subtle, often requiring precise viewing conditions to detect. The existence of rings around Uranus reshaped assumptions about planetary systems. What was once thought to be a singular feature of Saturn proved to be a more common phenomenon among giant planets. In Uranus's case, the rings do not dominate its appearance. They linger quietly, dark and narrow, tracing orbits that hint at past disruptions. Encircling a planet already defined by unusual orientation and magnetism, they add another layer to a world whose complexity often reveals itself only through careful observation. Encircling Uranus in carefully ordered paths, a retinue of 27 known moons moves through the tilted gravitational field of their parent planet. Unlike the satellites of other giants, whose names often draw from mythological pantheons, these moons carry titles drawn from literature. They are named after characters created by William Shakespeare and Alexander Pope, a choice that lends the system a quiet theatrical character, as though fragments of human imagination were set into orbit around a distant world. The 5 largest moons anchor this collection. Titania and Oberon trace wide paths far from the planet, their surfaces marked by impact craters and long fractures. Ariel and Umbriel circle closer in, each presenting a different expression of age and activity. Miranda, the smallest of the major moons, moves nearest among them, its surface bearing some of the most unusual terrain observed anywhere in the solar system. Together, these bodies form a diverse assembly shaped by both primordial formation and later transformation, composed primarily of mixtures of rock and ice. The moons likely formed from a disk of debris that surrounded Uranus after its early history of collisions and accretion. Water ice dominates their outer layers, mixed with silicate material and darker compounds that record exposure to radiation. The balance between rock and ice influences internal evolution. Larger moons retain more heat from their formation, allowing for the possibility of partial melting and internal differentiation, while smaller bodies cool more rapidly and preserve simpler structures. Voyager 2 provided the first close images of these satellites, revealing surfaces that ranged from heavily cratered plains to fractured landscapes carved by tectonic forces. Aerial displayed networks of valleys and ridges, suggesting that internal processes once reshaped its crust. Titania exhibited vast chasms stretching across its surface, evidence of expansion and stress within the moon's interior. Miranda's patchwork terrain, composed of contrasting regions with sharply different textures, hinted at episodes of disruption and reassembly or intense internal deformation. Umbriel appeared darker and more heavily cratered, its surface preserving a longer record of impacts with fewer signs of resurfacing. Oberon, farthest among the major moons, carried both ancient craters and signs of past tectonic movement. The variation among these bodies implies that their histories diverged, shaped by differences in size, composition, and orbital interactions. Tidal forces exerted by Uranus may have generated internal heating at certain periods, particularly if orbital resonances once amplified gravitational flexing. Over time, this heating could have driven geological activity, allowing subsurface layers to shift and fracture the icy crust. In some cases, the evidence suggests that liquids once existed beneath the surface. Perhaps transient oceans formed when internal temperatures rose above the melting point of water ice under pressure. Although direct confirmation remains beyond current observation, the structural features etched into these moons preserve a record of dynamic episodes long since concluded. The smaller satellites, irregular in shape and more numerous, likely include captured objects and fragments from past collisions. Their orbits and compositions add complexity to the system, forming a layered hierarchy of bodies bound to a planet already defined by unusual alignment and magnetism. Together, the 27 moons trace a miniature solar system of their own, each carrying scars and structures that reflect billions of years of quiet evolution in the shadow of a sideways giant. Among the satellites that circle Uranus, one appears as though it has endured a history too turbulent to remain hidden. Miranda, modest in size yet remarkable in detail, presents a surface unlike any other moon observed at comparable scale. When Voyager 2 sent back its images, the terrain seemed fractured into mismatched regions, as if assembled from pieces that did not originally belong together. Dominating this landscape are immense cliffs that rise to heights of nearly 12 miles, towering escarpments that dwarf most vertical features found elsewhere in the solar system. One of these, Verona Rupes, drops sharply across the surface, forming a wall of ice and rock that descends into shadow. Such structures imply powerful forces once reshaped the crust, lifting and splitting material on a scale disproportionate to the moon's small diameter. The broader terrain appears as a patchwork of contrasting provinces. Some areas are heavily cratered, preserving ancient impacts that date back billions of years. Adjacent to them lie smoother regions etched with ridges, grooves, and chevron-shaped bands. These younger surfaces suggest episodes of resurfacing, when internal activity altered the crust and erased older scars. The boundaries between these terrains are abrupt, as though different geological histories were stitched side by side. One leading interpretation holds that Miranda may have been shattered by a catastrophic collision early in its existence. In this scenario, a powerful impact fragmented the Moon, dispersing large portions of its mass into orbit around Uranus. Over time, gravity would have drawn the pieces back together, reassembling them into a roughly spherical body. The resulting structure would contain blocks of crust and mantle that formed independently before merging, explaining the jumbled appearance of the surface. Another possibility involves intense tidal heating during a past orbital resonance. If Miranda once moved in a gravitational relationship with neighboring moons that amplified tidal forces, its interior could have flexed repeatedly as it orbited. This flexing would generate heat through friction, partially melting subsurface ice and driving internal differentiation. As the interior warmed and expanded, stresses would fracture the crust, producing towering cliffs and complex tectonic patterns. Evidence for such internal heating appears in the network of faults and ridges crossing the surface. The presence of relatively young terrain, alongside ancient cratered plains, indicates that geological processes persisted long after the Moon's initial formation. The ice that composes much of Miranda's crust behaves differently under pressure than rock alone, capable of flowing slowly or fracturing sharply depending on temperature and stress. These properties allow for dramatic reshaping even within a small body. Miranda's low gravity accentuates the scale of its features. With weaker gravitational pull, vertical relief can grow more extreme without collapsing under its own weight. Cliffs remain standing where they might slump on a larger moon. The landscape thus preserves a record of forces that once operated beneath the surface, frozen in place as internal activity diminished. Today, Miranda circles quietly, its dramatic terrain illuminated by distant sunlight. The towering cliffs and patchwork plains remain as silent witnesses to episodes of disruption and renewal. Whether shattered and reassembled or reshaped by tidal heat, the Moon carries within its fractured surface the imprint of a dynamic past, revealing that even small worlds in the outer solar system can bear the marks of profound internal change. Farther from Uranus than Miranda, moving along a broader path through the tilted gravitational field, Titania carries a quieter presence. It is the largest of Uranus's moons, spanning more than 1,000 kilometers in diameter, and its greater mass has allowed it to retain a more complex internal history. Where smaller satellites cooled quickly and preserved simpler forms, Titania appears to have evolved through stages of subtle transformation. Voyager 2's images revealed a surface etched with long valleys and immense fault lines, some stretching for hundreds of kilometers across the icy crust. These chasms cut through older cratered terrain, forming networks that suggest global extension rather than localized disruption. The fractures are not random scars. They trace patterns consistent with a body that once expanded from within. As internal layers warmed and possibly differentiated, the outer shell would have been forced outward, cracking under tension. The composition of Titania is believed to be a mixture of rock and water ice, with rock likely forming a dense core surrounded by an icy mantle. During its early history, heat from radioactive decay within the rocky component could have raised temperatures sufficiently to alter the interior structure. If enough warmth accumulated, Ice in deeper layers may have melted, creating pockets or even extensive regions of liquid water beneath the frozen surface. As that liquid later refroze, expansion would have exerted stress on the crust above, generating the observed fractures. The possibility of a subsurface ocean rests on this thermal history. In recent years, models have suggested that certain icy moons in the outer solar system can retain internal oceans for billions of years, insulated by overlying ice and sustained by a combination of residual heat and antifreeze compounds such as ammonia. Titania's size makes it a candidate for such long-lived internal layers. Though direct evidence remains elusive, the presence of large-scale tectonic features implies that significant internal change once occurred. The surface itself bears the marks of time. Impact craters of varying sizes dot the landscape, some partially softened by later processes. In regions where faults intersect, the terrain appears rearranged, with blocks of crust shifted relative to one another. These structural displacements hint at a dynamic past in which the moon's interior was not entirely static. The interplay between rock and ice under pressure can produce complex mechanical behavior, allowing the crust to flex, fracture, and slowly reshape. Titania's orbital environment also plays a role in its evolution. Gravitational interactions with Uranus and neighboring moons generate tidal forces that subtly deform the moon as it travels. Although these forces are weaker than those acting on closer satellites in other systems, they may have contributed additional heating during earlier epochs when orbital configurations differed. Even modest tidal energy, applied over immense spans of time, can influence internal structure. Today, Titania presents a cold and distant exterior, its surface locked in ice and shadow for long intervals as Uranus moves through its prolonged seasons. Yet beneath that exterior, the memory of internal warmth remains inscribed in its fractures. Whether a liquid layer persists at depth or has long since solidified, the geological record suggests that Titania once held more than frozen stillness. It carries within its broken crust the imprint of expansion and change, a reminder that even far from the sun, large icy worlds can harbor histories shaped by heat concealed below. In January 1986, a solitary spacecraft crossed the outer reaches of the solar system and entered a realm no instrument had ever explored at close range. Voyager 2, launched nearly a decade earlier, approached Uranus after long journeys past Jupiter and Saturn, carrying with it cameras, magnetometers, and detectors designed to translate faint signals into understanding. Its arrival marked the first and, so far, only direct visit to this distant planet. As the spacecraft drew near, it captured images that replaced distant blurs with discernible detail. The pale disk resolved into subtle cloud bands and faint atmospheric features, more complex than early telescopes had suggested. Measurements of temperature, composition, and magnetic field flowed back across billions of kilometers, each packet of data adding depth to a world previously known only through inference. For the first time, Uranus was not merely a distant point of light, but a textured, measured environment. Voyager 2 confirmed the presence of the narrow ring system detected years earlier through stellar occultations. From close proximity, the rings appeared as dark arcs encircling the planet, sharply defined and more intricate than ground-based observations had revealed. The spacecraft also discovered additional faint rings and dust components, expanding the inventory of material orbiting Uranus. Alongside these findings came the identification of new moons, small bodies whose existence had remained hidden until the spacecraft's cameras resolved them against the background of space. The flyby trajectory was carefully calculated to maximize scientific return while preserving the spacecraft's ability to continue onward. As a result, Voyager 2 passed over the southern hemisphere during a prolonged seasonal phase. At that time, the southern pole was angled toward the sun, and the northern hemisphere lay in extended darkness. This geometry limited the viewing angle, leaving portions of the planet and its moons less illuminated or entirely unseen. Many regions were observed only under a single lighting condition, constraining the ability to interpret subtle topography and atmospheric variation. Despite these limitations, the dataset obtained during the brief encounter remains foundational. The magnetometer readings revealed the unusual tilt and offset of the magnetic field. Imaging instruments documented the fractured surfaces of moons such as Miranda and Titania. Plasma detectors characterized the surrounding magnetosphere and its interaction with the solar wind. Each instrument contributed a layer to the emerging portrait, transforming Uranus from a largely theoretical construct into a physically measured system. The encounter unfolded over a matter of days, with closest approach lasting only hours. After transmitting its final high-resolution images, Voyager 2 continued outward toward Neptune, leaving Uranus behind. The planet resumed its distant orbit, and the spacecraft's perspective became a memory preserved in digital archives and scientific publications. In the decades since, no orbiter has returned to refine or extend that snapshot. Telescopes on Earth and in orbit have supplemented the record, but they cannot replicate the intimacy of a close flyby. The measurements from January 1986 still anchor discussions of Uranus's structure, rings, and magnetosphere. A single passage, brief yet transformative, remains the most detailed chapter in humanity's direct exploration of this tilted world. When Voyager 2 departed the Uranian system in early 1986, it left behind a portrait both detailed and incomplete. The encounter had unfolded during a specific moment in the planet's prolonged seasonal cycle, when the southern hemisphere was angled toward the sun and bathed in continuous light. The northern hemisphere, by contrast, lay in extended darkness, hidden from direct view. Illumination, that quiet partner of observation, shaped what could and could not be seen. Images returned to Earth showed the southern regions under steady sunlight, revealing cloud patterns, subtle bands, and the outlines of major moons. Yet, the northern half remained largely uncharted, its terrain and atmospheric structure concealed by shadow. Instruments could measure magnetic fields and particle environments across both hemispheres, but visual data depended on reflected light. Entire latitudes were recorded only as faint silhouettes or not at all. The timing of the flyby also limited the ability to witness change. Voyager 2 passed swiftly through the system, its closest approach lasting only hours. While it gathered an extraordinary volume of information during that brief window, it could not remain in orbit to observe how the atmosphere evolved over weeks, months, or years. Seasonal transitions on Uranus unfold over decades, and a short encounter offers only a snapshot within that extended rhythm. Subtle atmospheric dynamics likely went unnoticed. Later telescopic observations have revealed transient bright storms and shifting cloud formations that were not apparent in the 1986 imagery. It remains possible that such features were either absent at the time or simply too faint under prevailing lighting conditions to stand out. The southern hemisphere's prolonged exposure to sunlight may have suppressed certain contrasts, while the northern hemisphere's darkness concealed others entirely. Surface details on the moons were also shaped by the angle of illumination. Regions of Titania, Oberon, and Ariel were captured in varying degrees of light and shadow, but portions remained beyond clear resolution. Miranda's dramatic terrain was revealed in striking clarity, yet even there, only one hemisphere received close inspection. Without repeated passes under different lighting geometries, the full extent of geological variation remains uncertain. The magnetosphere, though measured directly, was sampled during a single phase of its rotational and seasonal orientation. Given the planet's tilted magnetic axis and shifting magnetotail, long-term monitoring would be required to understand how the system evolves over extended periods. Voyager 2 provided a foundational data set, but it could not chart the full variability inherent in such a dynamic configuration. In the decades that followed, Earth-based and space-based telescopes have gradually illuminated the northern hemisphere as Uranus progressed along its orbit. New images have revealed cloud activity and brightness changes that were invisible in 1986. These observations hint at complexities that a brief flyby could not capture. The planet's long seasons mean that entire atmospheric patterns emerge and dissipate over spans far exceeding the duration of a spacecraft encounter. The 1986 visit thus stands as both revelation and reminder. It unveiled rings, moons, and magnetic peculiarities, yet it occurred at a moment when half the planet lay hidden. The data transformed understanding, but it also underscored the limits of a single pass through a system governed by cycles measured in decades. What was missed is not a failure of exploration, but a consequence of timing, of light and shadow, defining the boundaries of what could be known during that solitary journey. Long after the brief encounter of a passing spacecraft, Uranus returned to being a distant point of light, suspended at the threshold of visibility. Yet distance did not mean abandonment. From Earth's surface and from orbit above it, instruments continued to follow the planet's slow progression through space, assembling a record measured not in hours, but in decades. The Hubble Space Telescope, freed from atmospheric distortion, became one of the most consistent observers of Uranus. With its sharp resolution and sensitivity to ultraviolet and visible wavelengths, Hubble captured subtle variations in brightness and cloud structure across the planet's disk. Over time, sequences of images revealed that the pale atmosphere was not static. Faint bands strengthened or faded. Bright spots emerged, drifted with prevailing winds, and then dissolved back into the haze. Each image added a frame to a time lapse unfolding at planetary scale. On Earth, large ground-based telescopes equipped with adaptive optics extended this effort. By compensating for atmospheric turbulence in real time, these observatories achieved clarity once reserved for space-based platforms. Infrared cameras, in particular, offered a new perspective. At longer wavelengths, temperature contrasts become visible, allowing storms and atmospheric disturbances to stand out against cooler surroundings. Features that appeared faint in visible light sometimes glowed more distinctly in infrared, revealing activity hidden beneath upper haze layers. Through these observations, scientists began to track seasonal evolution across Uranus's long year. As the planet moved from solstice toward equinox, the distribution of sunlight shifted gradually between hemispheres. Telescopic records spanning decades captured corresponding changes in cloud patterns and brightness. Regions once subdued grew more active, while others settled into relative calm. The slow cadence of these transitions required patience. No single observing campaign could encompass an entire seasonal arc. Infrared spectroscopy also provided insight into atmospheric composition. By analyzing how different wavelengths were absorbed and emitted, researchers inferred the presence and distribution of methane and other trace gases. Variations in absorption patterns hinted at vertical mixing and localized upwellings. Even without a spacecraft in orbit, the interplay between light and matter carried information across vast distances, encoded in subtle spectral signatures. Ground-based radio telescopes and other instruments monitored emissions linked to the magnetosphere, complementing optical studies. Though less detailed than in situ measurements, these data contributed to a broader understanding of how the planet interacts with the solar wind over time. Together, diverse observing techniques formed a mosaic of partial perspectives, each revealing a different facet of a complex system. Watching from Earth requires sustained attention. Uranus advances slowly along its orbit, and meaningful change may unfold over years. Yet this extended timeline offers its own advantage. By revisiting the planet repeatedly, astronomers can detect trends that a brief encounter might miss. Patterns emerge gradually as brightness shifts accumulate and storm activity waxes or wanes in response to changing solar angles. The image of Uranus as a tranquil, featureless sphere has steadily given way to a portrait of measured dynamism. Through the combined efforts of space-based and ground-based observatories, the planet's atmosphere has been revealed as responsive and evolving, even at such great distance. Though no orbiter circles it, the quiet vigilance of telescopes continues, recording the slow choreography of clouds and light across a world whose seasons unfold at a pace uniquely its own. Across decades of observation, Uranus has remained a world defined as much by absence as by discovery. A single flyby provided a foundation, and telescopes have extended that view from afar. Yet many aspects of the planet and its system remain only partially resolved. In recent years, planetary scientists have increasingly turned their attention toward the possibility of returning, not with a passing spacecraft, but with an orbiter designed to remain. The concept of a Uranus orbiter and probe has emerged within major planetary science surveys as a high priority objective. These decadal assessments, which guide long-term exploration strategies, have recognized that Uranus represents both a unique system and a broader class of ice giant planets common beyond our solar system. An orbiter stationed around Uranus would offer sustained observation, allowing scientists to track atmospheric evolution, magnetic behavior, and moon interactions over extended periods rather than during a fleeting encounter. Such a mission would likely include an atmospheric entry probe, descending through the upper layers to measure composition, temperature, pressure, and wind structure directly. Remote sensing can infer these properties from spectral data, but in situ sampling would provide precision unattainable from orbit alone. By analyzing noble gases and isotopic ratios within the atmosphere, researchers could reconstruct aspects of the planet's formation history, identifying the materials present in the early solar nebula at its location. An orbiter would also map the magnetosphere in detail, following the shifting geometry of the tilted magnetic field over multiple rotations and seasonal changes. Instruments could measure charged particle populations, radiation belts, and auroral emissions with continuity. The interaction between the magnetosphere and the solar wind, previously sampled only briefly, could be observed across different solar conditions, revealing patterns that require time to unfold. The moons and rings would benefit equally from sustained study. High-resolution imaging across varying lighting angles would clarify surface composition, tectonic features, and potential evidence of subsurface layers. Repeated passes could detect subtle geological activity or changes in ring structure driven by gravitational interactions. Measurements of gravitational fields would refine models of internal structure for both the planet and its satellites, constraining the distribution of mass beneath their surfaces. Beyond the specific science objectives, a mission to Uranus carries broader implications. Ice giants are abundant in exoplanet surveys, often appearing in size ranges similar to Uranus and Neptune. Understanding the internal structure, atmospheric chemistry, and magnetic environments of our nearest example would inform interpretations of distant worlds whose properties are known only through indirect measurements. Data gathered in orbit around Uranus would serve as a reference for planetary systems across the galaxy. The journey to such a distant destination would require patience and engineering resilience, with travel times measured in years, yet the potential return is equally long-lived. By remaining in orbit, a spacecraft could witness the gradual transition of seasons, observe storm systems develop and fade, and monitor the magnetosphere's evolving configuration. The prolonged nature of Uranus's cycles demands observation measured in similar spans. In proposing a new mission, scientists are not seeking spectacle but continuity. The goal is to replace a solitary snapshot with a sustained narrative, to follow the processes that define this tilted world through the slow cadence of its orbit. In doing so, the enduring uncertainties surrounding its internal heat, magnetic asymmetry, and atmospheric behavior could be addressed with clarity grounded in direct measurement. Beyond the boundaries of our solar system, a quiet pattern has emerged in the catalog of distant planets. As telescopes detect subtle dips in starlight and measure faint stellar wobbles, a recurring category appears with surprising frequency. Worlds roughly comparable in size to Uranus, neither massive like Jupiter nor small and rocky like Earth, populate the data in significant numbers. These planets, often described as ice giants or sub-Neptune types, seem to be among the most common outcomes of planetary formation around other stars. In many observed systems, planets with radii between Earth and Neptune dominate the inventory. Their masses and densities suggest compositions rich in volatile materials, mixtures of rock, water, and thick gaseous envelopes. Though separated from us by light years, their measured properties echo those of Uranus. Some orbit close to their host stars, heated to temperatures far exceeding anything in our outer solar system. Others reside at greater distances, where equilibrium temperatures may be more moderate. Yet in bulk characteristics, they occupy a familiar range. This prevalence has reshaped the way planetary scientists view Uranus. Once considered an outlier in a system defined by larger gas giants and smaller terrestrial worlds, it now appears representative of a broader cosmic class. The structural features that make Uranus distinctive within our own system may in fact be typical on a galactic scale. Its mass, radius, and likely internal layering align with properties inferred for countless exoplanets detected by missions such as Kepler and TESS. Interpreting the atmospheres of distant ice giants relies heavily on models grounded in local examples. Spectroscopic observations of exoplanets can reveal the presence of hydrogen, helium, methane, water vapor, and other compounds, but these signals are faint and often blended. By studying how methane shapes the color and thermal structure of Uranus, researchers refine their understanding of how similar gases influence the spectra of faraway worlds. The physics of radiative transfer, cloud formation, and atmospheric circulation tested in our solar system becomes a template for interpreting remote data. Internal structure is equally significant. If Uranus possesses layers of water and ammonia under extreme pressure, possibly including exotic phases of matter, then analogous conditions may exist within many exoplanets of comparable size. The way heat is transported through such interiors, and the manner in which magnetic fields arise from conductive fluids, inform expectations for magnetic signatures and atmospheric escape in distant systems. Each detail gleaned from Uranus contributes to a framework applied across the galaxy. The orientation and seasonal behavior of Uranus also offer perspective. While extreme axial tilts may not be universal, dynamical histories involving collisions and orbital migration appear common in planetary systems beyond our own. Observations of exoplanet eccentricities and inclinations indicate that gravitational interactions can rearrange worlds long after their formation. The sideways posture of Uranus thus serves as a local example of how such interactions might imprint lasting consequences on a planet's climate and magnetic geometry. In this context, Uranus becomes more than a solitary curiosity. It stands as a bridge between the intimate and the distant, between direct measurement and indirect inference. By understanding its atmosphere, interior, and magnetic environment in detail, scientists gain a reference point against which to compare thousands of exoplanets whose features can only be glimpsed through subtle variations in starlight. The study of this tilted ice giant therefore extends far beyond its orbit, informing the interpretation of planetary systems scattered across the Milky Way. Beneath the pale clouds and muted light, Uranus conceals a structure that cannot be seen directly, only inferred through gravity, magnetism, and the subtle mathematics of planetary physics. The visible atmosphere is merely the outermost veil of a far deeper architecture, one arranged in layers shaped by pressure and composition rather than by solid ground. Models of the planet's interior suggest a stratified design. At the top lies the relatively thin envelope of hydrogen and helium, mixed with methane that filters incoming sunlight. Descending below this gaseous region, temperature and pressure increase steadily. The boundary between atmosphere and interior does not occur at a distinct surface, but through a gradual transition, where gas thickens into dense fluid. This fluid region is believed to extend thousands of kilometers downward, forming what is often described as a mantle rich in water, ammonia, and methane. Within this mantle, conditions depart entirely from familiar experience. Pressures rise to millions of times Earth's surface pressure, compressing molecules into configurations that no laboratory on Earth can easily replicate for long. Water, which at ordinary conditions freezes into crystalline ice or flows as liquid, behaves differently under such extremes. It becomes part of a hot, dense mixture that may resemble a global ocean of volatile compounds, though the term ocean only hints at the complexity involved. Ammonia, mixed with water under these conditions, can lower freezing temperatures and influence electrical conductivity. This blend likely forms a conductive layer capable of supporting the dynamo processes that generate the planet's magnetic field. The presence of such a layer provides a possible explanation for the unusual magnetism observed from afar. Rather than arising from a metallic hydrogen core, as in larger gas giants, Uranus's magnetic field may originate within this deep, volatile, rich mantle. At even greater depths, where pressure climbs further and temperatures soar, theoretical and experimental studies point toward an exotic state known as superionic water. In this phase, oxygen atoms arrange themselves into a lattice structure, while hydrogen ions move freely through it, carrying electrical charge. The material behaves neither as a conventional solid nor as a typical liquid, but as a hybrid that conducts electricity efficiently under extreme conditions. Laboratory experiments using high-pressure techniques have produced evidence that such a state can exist within the range expected inside ice giants. If superionic water occupies a substantial region of Uranus's interior, it would influence both heat transport and magnetic field generation. The mobility of hydrogen ions could sustain electrical currents in layers offset from the planet's center, contributing to the observed displacement of the magnetic field. At the same time, the arrangement of materials into distinct layers might limit convection, helping to explain the subdued outward flow of internal heat. Beneath these volatile rich regions, a denser core of rocky material is thought to reside, composed primarily of silicates and metals accumulated during formation. This core would anchor the planet gravitationally, though it remains inaccessible to direct observation. Its size and exact composition remain uncertain, constrained only by measurements of mass and radius. The interior of Uranus, therefore, remains a realm of inference and simulation, where physics under extreme pressure defines possibilities rather than certainties. Each layer, from hydrogen envelope to volatile mantle to potential superionic depths, contributes to a structure unlike that of gas giants closer to the Sun. Hidden beneath a calm exterior, these internal arrangements continue to shape the planet's magnetic behavior, thermal evolution, and enduring mystery. In laboratories on Earth, far from the cold expanse where Uranus orbits, scientists have attempted to recreate conditions that exist thousands of kilometers beneath its clouds. Using powerful lasers and diamond anvil cells, they compress tiny samples of water to pressures millions of times greater than those at Earth's surface. In fractions of a second, shock waves surge through the material, raising both pressure and temperature to levels that approach those expected inside an ice giant. Under these extremes, water ceases to behave in any familiar way. At ordinary conditions, water arranges itself into well-known phases, flowing as liquid or locking into crystalline ice. Under immense compression, however, theoretical models predicted a more exotic possibility. Experiments have now provided evidence that water can enter a state known as superionic. In this phase, the oxygen atoms settle into a fixed lattice, forming a rigid crystalline framework. Within that framework, the hydrogen nuclei detach from their usual positions and move freely through the structure. This dual character gives superionic water properties, unlike those of standard ice or liquid. The oxygen lattice resembles a solid, maintaining structural order even at high temperatures. Meanwhile, the hydrogen ions behave almost like a fluid of charged particles, migrating through the lattice and carrying electrical charge. The material conducts electricity efficiently, not because electrons flow as in metals, but because hydrogen ions travel through channels in the crystalline framework. Such a phase may occupy vast regions deep inside Uranus. As pressure increases with depth, water mixed with ammonia and other volatiles could transition into superionic form. The presence of this electrically conductive layer offers a compelling explanation for the planet's unusual magnetic field. Dynamo action depends on the movement of conductive material within a rotating body. If hydrogen ions circulate within a superionic mantle, they could generate magnetic fields that are offset and tilted, consistent with measurements taken during the 1986 flyby. The implications extend beyond magnetism. Superionic water would influence how heat is transported through the interior. The rigid oxygen lattice could restrict large-scale convection, while the mobility of hydrogen ions might allow for localized currents. This combination could help maintain stratified layers, contributing to the subdued outward flow of internal heat observed at the surface. The deep interior would not be a simple churning ocean, but a complex region where solid-like and fluid-like behaviors coexist. Laboratory results have strengthened confidence in this model. By measuring changes in reflectivity and conductivity under extreme compression, researchers have identified signatures consistent with superionic transitions. Although these experiments last only brief instants, they provide a window into the conditions that persist for billions of years inside an ice giant. The alignment between experimental data and theoretical predictions suggests that such exotic phases are not mere abstractions, but realistic components of planetary interiors. In this context, the term ice takes on an entirely new meaning. Within Uranus, ice is not a brittle crust, but a high-pressure state of matter that bridges solid and liquid, structure and motion. Superionic water, if present, would occupy a realm beyond ordinary experience, shaping magnetic fields and thermal evolution from depths no spacecraft has reached. Through the convergence of laboratory physics and planetary modeling, a hidden layer of Uranus begins to take form, defined by atoms arranged in patterns that challenge everyday intuition. Long before its seasons stretched into decades and its magnetosphere began its measured contortions, Uranus likely endured a moment of violent redefinition. In the early solar system, protoplanets moved through crowded orbits, crossing paths in a gravitational dance that sometimes ended in collision. For Uranus, one such encounter may have been decisive, not only altering its orientation, but reshaping its internal destiny. Computer simulations suggest that an impact involving a body roughly comparable in size to Earth could tilt a planet by nearly 90 degrees without completely dispersing it. Rather than shattering Uranus beyond recovery, such a collision may have transferred angular momentum in a way that forced the planet onto its side while leaving much of its mass intact. The energy released in that event would have been immense, briefly raising internal temperatures and redistributing material within. In the aftermath of such a collision, debris would not have vanished into space immediately. Fragments of the impacting body and portions of Uranus's outer layers could have formed a transient disk encircling the planet. Within this disk, gravity would gradually draw material together, allowing moons to coalesce from the remnants. The present regular satellites, orbiting in aligned paths, may owe their configuration to this ancient ring of debris. In this sense, the tilt and the moons become intertwined outcomes of the same formative episode. The internal consequences may have been equally significant. A major impact would have disrupted pre-existing layers, mixing volatile rich mantles with deeper material. As the planet cooled following the collision, new stratification could have emerged, with denser components settling and lighter materials rising. If this reorganization produced stable compositional gradients, it might have suppressed large-scale convection. Such suppression would limit the upward transport of heat, potentially explaining the subdued internal luminosity observed today. In this scenario, the lack of excess heat is not merely a passive characteristic, but the lingering imprint of a violent past. The collision that tipped Uranus sideways may also have sealed its interior into a configuration less efficient at releasing stored thermal energy. The planet would cool more quietly, its outward radiation diminished compared with gas giants that retained vigorous convection. The formation of a debris disk may also have contributed to long-term stability within the system. By reassembling into moons that orbit in near circular, equatorial paths relative to the planet's tilted axis, The debris would help establish a balanced gravitational environment. These moons, through tidal interactions, can dampen oscillations in axial orientation over time, maintaining the planet's unusual posture across billions of years. The same event that disrupted the original configuration may therefore have laid the groundwork for enduring equilibrium. Though direct evidence of this impact lies beyond current reach, the alignment of tilt, moon system architecture, and thermal behavior forms a coherent narrative. Each element, considered alone, appears unusual. Taken together, they suggest a shared origin in an ancient collision that altered the planet's rotation, reorganized its interior, and seeded the material from which its satellites formed. Uranus thus carries the possibility that catastrophe became preservation. The sideways orientation that defines its seasons, the muted internal heat that shapes its atmosphere, and the orderly procession of moons may all trace back to a single transformative encounter. In that distant epoch, disruption did not erase the planet's identity. It reshaped it into the quiet, tilted world observed today. There are worlds where weather erupts in towering plumes and vanishes within days, and there are worlds where change unfolds so slowly that a human lifetime captures only a fraction of a season. Uranus belongs to the latter. Its atmosphere does not react to sunlight with immediate fury. Instead, it absorbs, stores, and redistributes energy with patient restraint, as though time itself stretches within its layered clouds. When sunlight gradually shifts from one hemisphere to the other over the course of decades, the response is measured. The upper haze brightens or dims not in sudden flashes, but in subtle tonal adjustments that can take years to register clearly. Telescopic observations spanning multiple decades reveal these transitions as gentle variations in reflectivity, small changes in contrast between latitudes, and the gradual migration of cloud bands. The planet's face seems almost unchanged at first glance, yet careful comparison across years shows a steady evolution. This slow response is tied to the thermal inertia of the atmosphere. With limited internal heat rising from below, the energy driving circulation must come largely from the distant sun. At such a remove, sunlight arrives weakly, and its seasonal redistribution unfolds over intervals far longer than on Earth. The atmosphere adjusts gradually, as if balancing an equation with extraordinary deliberation. Temperatures shift by small increments, pressure gradients strengthen or weaken, and winds reorganize over spans measured in years rather than days. Storm systems too reflect this unhurried rhythm. Some bright cloud features have been tracked for extended periods, drifting across latitudes with steady persistence. Rather than explosive, short-lived disturbances, these formations can evolve slowly, growing in brightness over successive observations before fading just as gradually. High-altitude methane clouds may condense when local conditions align, then dissipate as circulation patterns subtly change. Each stage proceeds without haste, embedded within the broader seasonal arc. Long-term monitoring from space and ground-based observatories has revealed hemispheric asymmetries that develop over decades. As one pole emerges into increasing sunlight, its atmospheric activity can intensify, producing new cloud structures and shifts in wind speeds. Meanwhile, the opposite hemisphere, moving into extended shadow, may settle into comparative stillness. These changes do not overturn the planet's appearance overnight. Instead, they accumulate quietly, layer upon layer, until the overall character of a hemisphere has altered. Brightness variations recorded in different wavelengths provide additional clues. Infrared imaging can detect temperature differences and deeper cloud structures that visible light conceals. Over many years, These datasets reveal that Uranus is not static but dynamic on a scale that demands patience to perceive. The climate behaves like a system moving in slow motion, where cause and effect remain linked yet separated by long intervals. This tempo gives Uranus a distinctive identity among the outer planets, where others radiate excess internal heat that drives vigorous convection. Uranus relies heavily on the gradual redistribution of sparse solar energy. Its atmosphere responds as a vast reservoir, smoothing extremes and stretching transitions across decades. The result is not inactivity, but subtlety, a choreography of light and cloud that rewards sustained attention. In this slow unfolding, the planet offers a reminder that change need not be abrupt to be profound. Across years and decades, brightness shifts, storms form and fade, and hemispheres trade roles under the distant sun. The movements are deliberate, continuous, and enduring, composing a climate that advances with the quiet persistence of time itself. High above the hidden layers where pressure climbs beyond imagination, the atmosphere of Uranus traces wide, invisible rivers that circle the planet with steady force. These currents do not merely drift with the planet's rotation. In many latitudes, they move against it, flowing in retrograde motion, carving bands of wind that slide westward even as the world beneath turns east. Measurements gathered during the brief flyby in the late 20th century and refined through later telescopic tracking of cloud features revealed that these winds can exceed 500 miles per hour. Such velocities rival those found on larger gas giants, yet the context is different. Uranus lacks the strong internal heat that drives towering convection on Jupiter, and still its upper atmosphere sustains remarkable speed. The motion appears organized into zonal jets, broad belts of alternating direction that encircle the planet in parallel rings. These zonal winds resemble, at first glance, the banded circulation of Jupiter. Both planets display latitudinal stripes shaped by differential rotation, where equatorial regions and higher latitudes spin at varying rates, yet the similarities mask important contrasts. On Jupiter, internal heat surges upward, feeding turbulent storms that punctuate the jet streams. On Uranus, with far less internal energy emerging from below, the winds appear smoother, their boundaries defined more by gradual gradients than explosive convection. The retrograde dominance of the equatorial jet stands out. Rather than racing ahead of the planet's spin, the equatorial atmosphere lags behind, sliding in the opposite direction at extraordinary speed. At higher latitudes, prograde jets take over, creating a pattern of alternating flow that gives the planet a dynamic yet measured character. Each band maintains its course over long intervals, suggesting deep-seated stability in the circulation system. The source of these deep winds remains an active area of study. Some models propose that solar heating, unevenly distributed across hemispheres due to the planet's extreme axial tilt, generates pressure differences that propagate downward. Others suggest that residual heat trapped within interior layers may still influence circulation indirectly, even if the outward radiation is modest. The resulting wind system could extend far below the visible cloud tops, penetrating into denser regions where methane condenses and ammonia mixes with water in exotic states. Tracking these winds relies on careful observation of cloud features that drift across the disk. Bright patches and subtle contrasts act as markers, their movement measured over hours and days to calculate velocity. From Earth, this requires patience and precision, as the planet's distant position renders its details faint. Yet over decades, consistent patterns have emerged, confirming that Uranus is far from stagnant. Unlike the chaotic turbulence of more internally heated giants, the winds here convey a sense of disciplined persistence. They are swift but not erratic, powerful yet restrained within structured lanes. The absence of frequent large-scale storms allows the zonal jets to maintain clarity, like currents in a deep ocean where surface disturbances are few. In this layered atmosphere, motion coexists with quiet appearance. From afar, Uranus may seem subdued, its pale disk offering little sign of activity. Beneath that impression, however, the deep winds continue their circuit, carving invisible tracks around a tilted world. Their steady passage shapes temperature distributions, influences cloud formation, and contributes to the planet's evolving climate. The result is a system both familiar in its banded symmetry and singular in its retrograde strength, a reminder that even restrained worlds can host formidable motion. 17 hours is all it takes for Uranus to complete a single rotation, a brief interval for a world so distant from the Sun. Yet that rotation does not resemble the upright spin of most planets. Instead, the globe turns while lying almost on its side, its poles tracing wide circles through space, as though the axis itself had been gently tipped and left to endure. This nearly sideways posture reshapes the meaning of rotation. On many planets, the axis stands in modest inclination, allowing the equator to face outward in balanced measure. On Uranus, the axis leans by roughly 90 degrees, so that as it turns every 17 hours, regions near one pole may alternately point toward and away from the Sun in sweeping arcs. The daily cycle is superimposed upon a far longer seasonal rhythm, creating patterns of illumination and shadow that have no true parallel elsewhere. The strangeness deepens when the magnetic field is considered. Unlike the rotational axis, which defines the visible spin, the magnetic axis is tilted at a sharp angle relative to that rotation. Moreover, the magnetic field is offset from the planet's center, as if its dynamo were displaced within the interior. As Uranus rotates, the magnetic poles do not simply trace small circles near the geographic poles. They swing widely through space, describing complex paths that alter the shape and reach of the surrounding magnetosphere. This misalignment produces a magnetospheric environment in constant reconfiguration. Radiation belts, composed of charged particles trapped by magnetic lines, are carried along with the rotating field. Because the field itself is tilted and offset, the belts wobble dramatically, expanding and contracting as they sweep around. Regions of intensified radiation shift in position over the course of a single rotation, exposing different segments of space to varying levels of energetic particles. The interaction with the solar wind becomes correspondingly intricate. As streams of charged particles from the Sun encounter Uranus, the orientation of the magnetic field determines how and where that energy is deflected. With each 17-hour turn, the angle between the incoming solar wind and the magnetic axis changes substantially. The magnetotail, stretching far into space, twists into helical shapes as the planet spins, wrapping and unwrapping like a ribbon in motion. For any spacecraft venturing near, this shifting geometry would present a landscape that never quite repeats itself. Measurements taken at one moment could differ significantly just hours later, not because the solar wind has altered dramatically, but because the magnetic framework through which it flows has rotated into a new configuration. Radiation belts may intensify in one region while diminishing in another, their structure governed by the interplay between rotation and magnetic tilt. This rotation, swift yet strangely oriented, ties together the planet's physical identity. The sideways spin governs sunlight distribution, The magnetic offset reshapes the invisible shield around the planet, and the two combine to produce a dynamic environment that defies simple symmetry. Uranus does not merely turn, it turns in a manner that continually rearranges its interaction with space. Across the span of each 17-hour cycle, the planet completes a complex choreography of axis, magnetism, and motion. The result is a world whose rotation is not a straightforward spin but a layered movement, one that alters its radiation belts and magnetospheric boundaries with every turn. In that steady, tilted rotation, Uranus maintains a character unlike any other planet in the solar system, defined by geometry as much as by distance or composition. There is no horizon to land upon here, no hidden crust waiting beneath the clouds. A descent into Uranus would not end with a firm impact, but with a gradual surrender, as gas thickens into fluid and fluid deepens into something denser still. The boundary between sky and interior is not a line, but a slow transformation, a continuum of pressure and composition that resists simple definition. From afar, the planet appears as a smooth sphere, its pale cyan surface suggesting calm solidity. In truth, that visible surface is merely the uppermost veil of an atmosphere composed primarily of hydrogen and helium, enriched with methane and trace compounds. Beneath the highest haze layers, pressure increases steadily. Temperature rises in response, and gases begin to behave less like airy vapor and more like compressible fluid. There is no moment when one could say the atmosphere has ended and the interior has begun. As depth increases, clouds of methane give way to layers where other compounds condense. The chemistry shifts with pressure, and the physical properties shift with it. Hydrogen, under sufficient compression, approaches states that blur the distinction between gas and liquid. The planet's gravity ensures that each descending kilometer multiplies the weight pressing inward. What begins as a gentle gradient soon becomes an overwhelming force. At tens of thousands of atmospheres, materials familiar at Earth's surface enter unfamiliar regimes. Molecules pack tightly, their interactions dominated by compression rather than temperature alone. Deeper still, water and ammonia may mix into vast, dense layers, forming high-pressure fluids that conduct electricity and participate in the generation of magnetic fields. Yet even here, there is no solid ground in the ordinary sense. The interior may contain a rocky core at extreme depth, but it lies far below layers that would crush any structure long before arrival. A hypothetical probe released into this environment would encounter mounting resistance almost immediately. Instruments designed to withstand modest planetary atmospheres would fail as pressure climbed beyond their limits. Structural components would deform under the load, electronics compromised by heat and compression. Even if engineered to survive far deeper than current designs, the descent would end in destruction well above any central core. The gradual thickening of the atmosphere ensures that the probe would not strike a surface, but would be overwhelmed by pressure before reaching a definable boundary. This absence of a solid surface challenges the imagination shaped by terrestrial experience. On Earth, mountains rise from continents and oceans rest upon crust. On Uranus, clouds transition into fluids without interruption. The concept of landing loses meaning. Instead, the planet invites the notion of immersion, of sinking ever deeper into a world where density increases without offering foothold. Such structure is characteristic of ice giants, yet Uranus expresses it with particular subtlety. The gentle visual appearance conceals an interior that grows progressively hostile with depth. There is no dramatic break, no cavern or chasm marking a shift from sky to ground. The transformation is continuous, governed by physics rather than landscape. In this way, Uranus remains a world defined by gradients. Light fades through haze, pressure intensifies through unseen layers, and matter itself transitions from gas to fluid to exotic states under crushing force. The absence of a solid surface does not render the planet incomplete, it defines its identity. Uranus is not a place to stand upon, but a realm to descend into, where each step downward becomes a surrender to pressure and transformation. On rare nights, far from city lights and under steady, transparent skies, a faint point can be seen drifting among the stars, barely distinguishable from them. It does not blaze like Venus or glow red like Mars. It offers no rings to the naked eye, no shifting bands of color. And yet that dim speck is a giant planet, the farthest world visible without optical aid under ideal conditions. For much of human history, Uranus passed unnoticed, blending seamlessly into the starfield. Its slow motion across the heavens escaped recognition until careful observation revealed that one of those fixed points was wandering. Even after its identification, it remained subdued in cultural imagination. Jupiter commands attention with its brightness and size. Saturn captivates with its rings. Neptune intrigues with its storms and deep blue hue. Uranus lingers quietly at the edge of perception, seldom occupying center stage. This quiet presence extends into the history of exploration. Only one spacecraft has ever visited, a single flyby that occurred decades ago. That brief encounter transformed Uranus from a distant abstraction into a measured world with rings, moons, and a complex magnetic field. Yet the spacecraft did not linger. It swept past and continued outward, leaving behind a planet still largely unknown. Every detailed map, every profile of its atmosphere, every glimpse of its moons traces back to that fleeting passage. Since then, understanding has advanced through distant observation. Telescopes in orbit and on mountaintops have monitored its changing atmosphere, traced the movement of clouds, and refined measurements of its rotation and tilt. These efforts have deepened knowledge, yet they cannot replace sustained close exploration. No probe has descended through its atmosphere. No orbiter has surveyed its magnetosphere over time. No lander has studied its moons from the surface. The giant remains, in many respects, a frontier. There is a paradox in this isolation. Uranus is immense, larger than Earth by many times in diameter and mass, yet it stands at the margins of attention. Its distance from the Sun makes missions lengthy and costly, its subdued appearance less dramatic than its neighbors. And so it waits, orbit after orbit, completing years that span decades on Earth, while human curiosity circles more familiar targets. Yet the significance of Uranus extends beyond its solitude. Ice giants appear to be common throughout the galaxy, based on observations of distant planetary systems. To understand Uranus is to gain insight into a class of worlds that may populate countless stars. Its composition, interior structure, and atmospheric dynamics represent not anomalies, but potentially widespread planetary forms. In this sense, its quiet existence carries broad implications. The lone flyby in human history offered a first chapter, not a conclusion. It revealed enough to hint at complexity, enough to show that beneath the pale disk lies a dynamic and layered system. The rest remains unwritten, awaiting instruments that can endure the journey and linger long enough to witness change. In the vastness beyond Saturn, Uranus continues its sideways spin, distant yet visible to patient eyes. It stands as the loneliest of the giant planets, not because it lacks companions or motion, but because it has received so little sustained attention. A world of immense scale, shaped by ancient collisions and governed by subtle forces, still waits to be understood more fully. Its faint light, a quiet reminder of how much remains beyond the reach of familiarity. Some planets confirm expectations, others quietly unravel them. Uranus belongs to the second kind. With every layer examined, every measurement refined, it resists easy classification, pressing against the boundaries of the models designed to explain how worlds form and evolve. Classical theories of planetary formation describe giant planets assembling beyond the frost line, where volatile compounds condense into solid cores that later capture thick envelopes of gas. Jupiter and Saturn fit comfortably within this framework, their immense gravity and strong internal heat aligning with predictions. Uranus does not conform so neatly. Its comparatively low heat output, extreme axial tilt, unusual magnetic geometry, and subdued atmospheric appearance complicate the standard narrative. The planet appears to have followed a different evolutionary path, or at least to have experienced events that altered its trajectory in fundamental ways. The possibility of a massive impact reshaping its interior challenges assumptions about how stable giant planets remain after formation. If Uranus endured a collision capable of tipping it nearly onto its side, then early planetary systems were more dynamically violent than simplified models once implied. Such events would not be rare anomalies, but integral chapters in the construction of mature systems. Understanding Uranus, therefore, informs not only its own history, but the broader story of planetary architecture across time. Its muted internal heat further complicates theoretical expectations. Gas giants radiate excess energy long after formation, sustained by gradual contraction and residual heat from accretion. Uranus, by contrast, emits little additional energy beyond what it receives from the Sun. This discrepancy forces reconsideration of how internal layering, compositional gradients, and heat transport operate in intermediate mass planets. The interplay between structure and thermal evolution becomes more intricate, less uniform, demanding refinements in simulation and theory. Beyond our solar system, the significance expands. Surveys of distant stars reveal that planets in the size range of Uranus and Neptune are among the most common types discovered. Many orbit far closer to their stars, while others occupy distant orbits reminiscent of our own ice giants. In either case, Uranus serves as a nearby laboratory for interpreting worlds that cannot be examined in detail. Spectral signatures, atmospheric compositions, and internal models developed here become templates for understanding planets light years away. The strangeness of Uranus thus transforms from curiosity into context. Its sideways rotation, unconventional magnetosphere, restrained heat flow, and layered interior offer variations on a planetary theme that may be widespread in the galaxy. Each unusual feature challenges the tendency to generalize from a limited sample. Each anomaly encourages broader thinking about what is typical and what is exceptional among giant planets. As instruments improve and models grow more sophisticated, the planet's complexity deepens rather than diminishes. Observations reveal subtler cloud structures, more intricate wind patterns, and magnetospheric behaviors that resist simple explanation. Instead of resolving its mysteries completely, study often reveals further nuance. The clearer the image becomes, the more intricate the portrait appears. And yet the full picture remains unfinished. One flyby cannot capture seasonal cycles that span decades, nor map interior structures that require sustained measurement. Theories remain provisional, without new data to test them directly. Uranus continues its quiet orbit, holding within it answers that refine our understanding of planetary formation, impact history, and evolution on a cosmic scale. In its strangeness lies its importance, not because it is odd for the sake of novelty, but because it stretches the framework through which planetary science interprets the universe. Uranus stands as a reminder that diversity is not deviation, but reality, and that in studying the outliers, the broader pattern of worlds becomes clear.